Hi folks, welcome back to Physics with Captain Rod. Making this video here to try to demonstrate how to analyze a circuit, a very simple DC circuit where you have multiple elements hooked in parallel. So what we're looking at here, imagine we've got this 12 volt battery and we're going to run a pair of light bulbs here. And for the sake of example, let's imagine that this light bulb here has 2 ohms of resistance to it, and this light bulb here has 3 ohms of resistance. And we're going to imagine that these bulbs are hooked in parallel, which might look something like this, where these are connected like so, and then maybe over to here. Then these other sides are connected, and back to the battery. So this is an example of a parallel combination. And what basically makes it in parallel, and it'll be more clear here in a minute when I do the circuit diagram, but it has to do with the voltages across the resistors. What I like to do with a lot of these circuit problems is I like to color code the voltages. So this right here is the positive terminal of the battery, and this is all conducting material up to this point, here and here. So if I kind of color code that, this is all one potential. And the reason this is one potential, this is conducting material. And if you haven't seen my videos that I call the IFAC videos, important facts about conductors, one of them is that the conductor itself is an equipotential. So that means since this is wire and all conducting material, this is all one potential up to this point. On the other side of the fixture here, this wire, this is all connected, all conducting material, so this is all one potential. So when you look at your battery, you notice red to black, that's a 12 volt potential. And when we look at our bulbs, it's red to black across this bulb, red to black across this bulb. So that's the defining characteristic of what's called a parallel combination, that the voltage across these bulbs are the same. So what I'm going to do now is I'm going to draw what's called the circuit diagram, and I'm going to start with the battery. So it doesn't really matter where you put the battery. I'm going to go ahead and just kind of mimic this picture as close as I can. So here's my voltage symbol for the battery. Then I have a resistor here, a light bulb, which has a resistance. So this resistor here is going to represent this light bulb with a 2 ohm resistance. Now you notice there's also kind of a break off going to another one here. So I'm going to go ahead and kind of break off going to another one of 3 ohms of resistance. These guys come together back to the bottom of my voltage source here. Now, some subtle things about this, like where this wire is connected. It doesn't really matter if I draw it like this or like this or like this. This just needs to be connected somewhere between this voltage and this resistance. That would be equivalent to here, somewhere in this region. The other side of this picture, I tend to make mine kind of look like this, but like this wire here, I could have connected it anywhere along here, like this would have been perfectly acceptable as well. But so here's my picture. This long guy represents the positive terminal of the battery, the short guy the negative terminal, and that is a 12 volt potential difference between them. I like to color code my potentials. Again, this is all conducting material up to this point, so this is all one potential. I'm going to go ahead and color code that red. You will, however, get a potential drop across the light bulb here. Other side, this is all one potential as well. I'm just going to leave it as black. Key characteristic here, the potential red to black is a 12 volt potential. And as I look over here, red to black across this resistor, red to black across this resistor. So actually I'm calling them resistors. These are the light bulbs with a 2 ohm resistance and a 3 ohm resistance. Important fact, red to black is 12 volts. So that tells us there's a 12 volt potential here and a 12 volt potential here. That allows me to apply Ohm's law at each of these light bulbs. So Ohm's law, voltage equals current times resistance. It is a 12 volt potential across here. The resistance is 2 ohms. If I go ahead and solve that for the current, I get 6 volts over 2 ohms, which is 3 volts per ohm, and a volt per ohm is an amp. 3 amps of current through this resistor. That reminds me, going back to the picture, really, I should have drawn my currents first. We're going to get a current in this direction across this resistor. That's the one I just found. I might give this a name, like let's call it I1 for the current through the first resistance area here. We're going to have another current in this branch. They are not necessarily going to be equal. In fact, they're not going to be, so they should have different names. I might call that something like I2. If I back up here, we're going to have a current in this branch. I'm going to go ahead and call that, I'm going to call it I sub B for current in the battery branch. The current directions are dictated because the red is the higher potential part of the circuit, and current always goes from higher potential to lower potential, assuming positive charge carriers. So the current I found here was I1, 3 amps. We can find I2 by applying Ohm's law again. I'll do that right here. So voltage equals current times resistance. Again, the voltage across here, still 12 volts. The current is I2. We'll know that in a moment. The resistance is 3 ohms. And if we solve this for I2, we get 4 volts per ohm, or 4 amps. Now let's take a look at the current here coming from the battery. So right here we have a junction. And if you look at my picture, I1 is coming out of the junction. If you backtrack this, I2 is coming out of the junction as well. Current follows basic conservation law. Charge just can't disappear. That means whatever comes into this junction, which I'm calling I sub B here, that has to go out, which is the sum of I1 and I2. And if I take the, let's see, what did I get before here? 3 amps, and I add 4 amps, we get 7 amps. So we've got the current in every part of the circuit. So looking back at the original, we know that the current in this region here, anywhere from, let me do this in green, anywhere from here through the bulb to here, that current is the one I called I1. That's the 3 amps. Through the second bulb, that's any current that's good in this region right here. That's the one I called I2. That one is 4 amps. And then the one I called IB, that current is good anywhere in this region. And that's the one that's 7 amps. All right, in addition to the current calculations, I also wanted to demonstrate how to calculate the powers. So power can be calculated either by current times voltage or by I squared R. I'm going to go ahead and use current times voltage. So at this resistor here, the current is 3 amps. The voltage, red to black, is 12 volts. So we're going to get 36 watts out of that. Amp is a coulomb per second, and a volt is a joule per coulomb, so that works out to joule per second, which is a watt. Power at the second bulb, we're going to have the current, I2, 4 amps, times, now the voltage is still red to black, so that's still going to be 12 volts, 48 watts. And the total power, just like you might think, is the sum of the two. 36 watts plus 48 watts, which is, what is that? 84 watts, I believe. Let me think about that for just a minute here. 614. Yeah, 84 watts, I believe that is. So anyway, I wanted to make this video just to demonstrate, how to take a physical problem like this and draw the circuit diagram for it. You want to draw currents in as well as the resistors. Make sure that the currents are pointed from higher potential to lower potential. And again, here in this picture, this red is the highest potential part of the problem. So I've got currents going this way here across this resistor because red is higher potential than black. The currents go this way, again, because red is higher potential than black. You can apply Ohm's law at each resistor here, taking note of the fact that these are in parallel, so the voltages are the same, red to black, 12 volts, red to black, 12 volts. Apply Ohm's law, get the two currents, and then take note of the fact that at this junction here, the current going in, whatever you want to call it, is equal to the current going out. In my case, that's I1 and I2. And that's pretty well it. Hope this video demonstrates how to work these very simple circuit problems. Have a great day.